Hi, everybody. So now we're going to put our definition of relations to work and introduce a really fundamental notion in mathematics, which is the idea of an equivalence relation. And the idea behind an equivalence relation is that, let's say you're studying some collection of objects, whatever they are. Could be numbers or, I don't know, books or cities or whatever. And there's some property of those objects that you want to focus in on, and you want to forget about everything else. So let's say, you're interested in cars, but you only care about the number of cylinders that their engines have. Or you're interested in houses, but all you care about is the price of the house. And you'd like to sort of treat all cars with the same number of cylinders or all houses with the same price as if they were the same. And equivalence relations gives you a tool for doing that. It gives you a way to take a set and collapse it down into a smaller set where the objects in the smaller set are characterized by some property of the things in the bigger set. And this comes up in all branches of mathematics, and it's abstract, but a powerful idea. So let's see. Let's take a look at some examples of this and see how it works. Okay, so let's start with the definition. What is an equivalence relation? An equivalence relation is a particular kind of relation. So remember, a relation is just a subset of the Cartesian product of a set with itself. Just as a little reminder, if A is a set, a relation is just a subset of the Cartesian product, and we write that A is related to B if the ordered pair AB is in this subset R. So R is the collection of things which are related. And in the previous video, we talked about some properties of these relations, the reflexive, symmetric, and transitive properties. So let's remember a reflexive property. The reflexive property means that for all A and A, the pair AA is in R. Or put another way, ARA. And the symmetric property was a property of pairs. It said for all pairs AB in A, if AB is in R, then BA is in R. In other words, ARB implies BRA. And finally, there was the transitive property, which was a property of triples. It said for all triples A, B, C in A, if A, B is in R, and BC is in R, then AC is in R. So we have a property of one element of A, two elements of A, and three elements of A with respect to this relation. And an equivalence relation is a relation which satisfies all three of these properties. It's reflexive, it's symmetric, and it's transitive. And of course, the ultimate equivalence relation, or the most standard one, is just equals, right? Equals is an equivalence relation because certainly A is equal to itself. If A equals B, then B equals A. And if A equals B and B equals C, then A equals C. So maybe that's the most important thing to remember. And of course, what is this? I didn't mention this last time, but what is the R for equals? Well, it's just the collection of things of the form AA, where A is in the set A. In other words, the only things which are related to one another by the equals relation are the thing itself. So this is maybe the most basic of all equivalence relations. But there are lots and lots and lots of others. if we take a very simple finite set, -2, -1, 1, 2, 3, and 4, well, then as I already mentioned, equals is an equivalence relation. But we could also look at the relation has the same parity as. So the same parity means either both odd or both even. And it's certainly true that, let's just check, same parity. Is it symmetric? Yes, because everything has the same parity as itself. Is it sorry, that's reflexive. I always get those mixed up. Is it symmetric? So it is reflexive. Is it symmetric? If A has the same parity as B, does B have the same parity as A? Sure. Because if A and B have the order doesn't matter. And finally, transitivity. If A and B have the same parity, and B and C do, then A and C do. So if A and B are both even, if A and B are both even, and B and C have the same parity, then C must be even, and so then A and C have the same parity. They're both even. And the same thing can be done with has the same sign as. I mean, if two numbers are, if A and B, first of all, A always has the same sign as A. If A has the same sign as B, then B has the same sign as A. And if A has the same sign as B and B has the same sign as C, so then A has the same sign as C. We could check that one out for sign. Let's just check transitivity. So if A is positive and B is positive, and B is positive and C is positive, that implies that A is positive and C is positive. And if A is negative and B is negative, and B is negative and C is negative, then that certainly implies that A is negative and C is negative. And I think those are the only ways that A and B can have the same sign, is if they're either both positive or both negative. So having the same, and if you combine the relations by taking both of them, then you still get an equivalence relation because you can check the two properties separately. So this is a kind of a trivial example, but it at least gives you something to try out. Here's an example that doesn't use numbers. The book's examples mostly use numbers, but for example, let's take the set of books in Babbage Library that have only one author. So X is the set of books with only one author. And here are some equivalence relations. We could say that the two books are related if they have the same author. And that's an equivalence relation because every book has the same author as itself. If book A and book B have the same author, then it doesn't matter which order you say that in. And if book A has the same author as book B, and book B has the same author as book C, then they all have the same author, so book A has the same author as book C. Or you could use the fact that they have the same number of pages to make a relation. Or you could say that they're on the same floor of the library. And notice that what's going on in each of these things is that we're taking the book, which has many properties. It's color, title, author, publication date, number of pages, the language it's written in, and we're just picking out a property like the name of the author or the number of pages or where it is in the library. And we're saying two books are related if that one property is the same for both of them. And that's how an equivalence relation works. It allows you to focus your attention on one Now, what makes equivalence relations really pay is the idea of an equivalence class. So remember I said that equivalence relations allow you to pick a property of elements of a set and then focus in on that property. An equivalence class is what happens when you take that property and you put everything together if they are the same for that particular property. So as an example of our book example, remember we had books and we had the relation that they have the same number of pages. If we take a particular book and we take all the books that have the same number of pages as that particular book, that's the equivalence class of that book under that relation. So it's like we forget everything else about the books except how many pages they have, and we put all the ones that have the same number of pages as a particular book into a bag together. That's the equivalence class of that. So more formally, suppose we have a set and we have a relation on it, and I should be very careful to say an equivalence relation, otherwise this doesn't work. So R has to be an equivalence relation. And then, meaning symmetric, transitive, and reflexive. Now, suppose we choose an element of the set. We define the equivalence class of that element to just be all the elements of the set which are related to A under our equivalence relation. And sometimes if we have several relations floating around, we may decorate this with an R so we know what the relation that we're using is being referred to here. Notice just one very simple thing, that A, the element A, is always in the equivalence class of A because of the reflexive property, right? ARA is true, and therefore A belongs to the equivalence class of A because the equivalence class of A is everything related to A under R. So just to make this concrete, if we go back to the set -2, -1, 1, 2, 3, 4, and we use the relation has the same parity, what is the equivalence class of -2? Well, it's everything in this set A which has the same parity as -2. So that's -2, 2, and 4. What about the equivalence class of 2? Well, it's everything in this set which has the same parity of 2 as 2, and that happens to be -2, 2, and 4 again. So -2, the equivalence class, is the same as the class 2, equivalence class of 2. 1 is everything which has the same parity as 1, and that's going to be -1, 1, and 3. And similarly, 3, everything which has the same parity as 3, is going to be -1, 1, and 3. So one thing to notice about this is there's really only two equivalence classes. There's one equivalence class which consists of all the even ones, and one equivalence class which consists of all the odd ones. And so by looking at equivalence classes, we've focused in our attention in this set A onto just these two things, even and odd, and we've sort of put together all the even ones and all the odd ones. Let's look at a few more examples of equivalence classes, because this is really a crucial idea. So let's go back to our set of books and assume they have only one author, and let's let R be the relation has the same author. So then we have an equivalence class associated to the author Ray Bradbury. It'll be the set of books in Babbage Library with only one author, and that author is Ray Bradbury. If the relation is the same number of pages, and we take the book War and Peace, then the equivalence class of War and Peace is the set of books in Babbage Library, which have one author, that have the same number of pages as War and Peace. Now, why am I so hung up about this notion of having books with one author? Well, suppose you have a book you allow books with multiple authors, and suppose your relation R is two books are related if they have an author in common. So in other words, book A might be written by Teitelbaum and Frankenstein, and book B might be written by Frankenstein and Igor, right? Then they have an author in common. So book A is written by Teitelbaum and Frankenstein, my cousin. And book B is written by Frankenstein and his assistant, Igor. And book C, let's say, is written by Igor and Kaufman. So book A and book B have an author in common. And book B and book C have an author in common. But book A and book C do not have an author in common. So this is actually not an equivalence relation. It's not transitive. And so to avoid this problem, I limited myself to books with only one author so that I could be sure having the same author is an equivalence relation. Because if book A has the same author as book B and they only have one author, and book B has the same author as book C and they only have the same one author, then book A and book C have the same author. So we avoid this problem. Here's another example, this one taken from the text. Let's look at the set of polynomials with real coefficients. And we're going to say that two polynomials are related if they have the same degree. So remember, the degree of a polynomial is the highest power of x which occurs in the polynomial. And if the polynomial is a constant, we say it has degree 0. This is an equivalence relation. It's easy to check that. Maybe maybe we'll go through it. So if polynomial 1 and polynomial 2 have the same degree, transitivity is the key one. If f and g have the same degree, and g and h have degree n, well, this means that f and g both start with x to the n, maybe ax to the n plus lower order terms, and g starts with bx to the n plus lower order terms, and h starts with cx to the n plus lower order terms. So therefore it's clear that f and h have the same degree. So it is an equivalence relation. I didn't check reflexivity and symmetry, but hopefully you believe that. So what is the equivalence class of the polynomial x? Well, it's the equivalence class of x is the set of all polynomials f which are related to x, which is the same thing as saying the set of all polynomials of f such that the degree of f equals the degree of x, which is the same thing as the set of polynomials f such that the degree of f is 1. So all the polynomials of degree 1 are in the equivalence class of x. More generally, suppose you took another polynomial of degree 1, like x plus 3. Well, the same thing would be true. The equivalence class of that polynomial would also consist of all polynomials of degree 1. And the effect of this equivalence relation is to divide up the set of polynomials by their degree. You have the equivalence class of polynomials of degree 1, and of degree 2, and of degree 3, and of so forth. So if you were interested in studying the degree of polynomials, and you don't care about anything else about them, in a certain sense you would just be focusing in on these equivalence classes. And now I have one more really fundamental example that we've seen before. We already showed that congruence mod n is an equivalence relation on Z. What are the equivalence classes in that case? Well, let's remember that x is congruent to y mod n. That means that n divides x minus y. And that means that x minus y is k times n for some k. In other words, x is equal to y plus kn for some k. Well, we could look at an example. Let's let n be 3, and let's look at the equivalence class of 1. This is the collection of x's such that x is congruent to 1 mod 3. Well, by this little calculation here, that's equal to the set of x's such that x equals 1 plus 3k for k and z. And we know what this set is. This is the set, well, I'll write out some elements. Depending on what k is, it's 1, 4, 7, 10. But we could also go backwards, minus 2, minus 5, minus 8, and so on. As k moves through z, these numbers step by 3, but they start at 1 and they go in both directions. So the equivalence class of 1 consists of all the numbers of the form 3k plus 1 as k runs through the integers. This is if we're working mod 3. The equivalence class of 2, well, it's similar. It starts at 2 and it goes by 5, 8, and so on, but also downwards. And finally, the equivalence class of 0 is just the multiples of 3. So these sets are arithmetic progressions. Every number is either congruent to 0, 1, or 2 mod 3. So every number is going to be, I mean, for instance, if we took the equivalence class of 7 mod 3, well, it's going to be exactly the same as this one, because it's going to be everything of the form 7 plus 3k, but that's the same thing as the set of things of the form 1 plus 6 plus 3k, which is the set of things of the form 1 plus 3 times k plus 2. So as k runs through z, k plus 2 runs through z, and so you're going to get exactly the same set. So the equivalence classes under congruence are the arithmetic progression where the step size is n. Let me make another page here. I think I can do that because I think we need to say a little bit more here. So let's go back to congruence as continued here. So more generally, if we take the set, we take n is an arbitrary integer, n is an arbitrary natural number, and we take the equivalence class A, which is the set of A, x congruent to A mod n. This is equal to the set of x which are equal to A plus kn for k in z, which is the arithmetic progression of the form A plus n, A plus 2n, A minus n, A minus 2n, A minus 3n, and so forth. So the equivalence classes are these arithmetic progressions with step size of n, and there are n different equivalence classes, because if you pick, they correspond to 0, 1 up to n minus 1, because if we picked, let's say, another number, it's going to fall into one of these arithmetic progressions in the same way that when we looked back here, since 7 is in the arithmetic progression based at 1, if you start the arithmetic progression at 7, you're going to get the same collection of numbers. So the congruence relation divides up the integers into n arithmetic progressions. And we're going to look at this example more closely again. And then just to give you one other example, the rational numbers can be thought of as constructed from equivalence classes. If we take a pair mn, where n is not 0 and m and n are integers, and we make the equivalence relation where mn is equivalent to m prime n prime if m n prime minus m prime n equals 0. So what's the equivalence class of the pair mn? Well, it's the collection of all pairs m prime n prime where mn prime minus m prime n equals 0. And where did I get this? Well, this is this cross multiplication. This says that mn prime equals m prime n, or in other words, that m over n equals m prime over n prime. And this is legit because n prime is n and n prime are not 0. That's part of the rules by the definition of the set. So the equivalence class Mn is all of the pairs of numerators and denominators that give the same fraction, m over n. So for example, the class of the pair 1, 2 consists of 1, 2, 2, 4, minus 2, minus 4, minus 3, minus 6, and so on. It's all possible, and these are all in the same equivalence class because in each case, 2/4 is 1/2, minus 2 over minus 4 is 1/2, minus 3 over minus 6 is 1/2, and so on. And what's interesting about this is that this gives you a way to define the rational numbers without ever actually having to say what a fraction is, because this is just an integer calculation. You say you take the set of pairs m and n, where mn prime minus m prime n equals 0, and you get a set which is the same, the equivalence classes of which are the same as the rational numbers, each equivalence class consisting of, for a single rational number, all of the different ways you can write it as a fraction, not necessarily in lowest terms.